Hi, this is Zibo, and my project is on learning intertime parameter drift in self-tuning regulators. So I want to address a fundamental question that I'm interested in studying for a while. That is the still parameter observations in adaptive control. So in adaptive controllers, what you're often doing is that you're taking the past parameter estimate and use it as if it's your fresh parameter estimate. You do so because you only know what the current system parameters are after you have observed the output and computed your current input. However, you need your current input and the fresh parameters to compute the accurate output. So you're sort of in a loop of dilemmas here. So in this project, I want to see if I can find a way to solve that. So we in this project, we want to take advantage of iterative systems to eliminate the controller lag. We do so by adapting the following assumptions. We assume that there is a ground truth set of parameters, system parameters theta across time, but that stays constant across iterations. And then we're not going to model the exact parameters, however, we're going to model the drift, so the deltas, the differences between two sort of adjacent parameter thetas, so theta k and theta k plus 1. We want to run some sort of an inference model that moves from theta 0 to theta 1 to theta 2 to theta 3 all the way in the time domain using all these deltas. And then we want to run the iteration again and again and again so that sort of along the trials, the deltas, they converge to their ground truth value from some initial probability distribution. So effectively, we have the classic STR setup, and we maintain the following things within any iteration. We maintain a prior belief over theta 0. So this is a probability density function of representing our belief of what the initial state in time is. And then we have a belief of each of the deltas. In the previous slide, we assume that there is a ground truth value for the delta. However, in our process, we maintain a PDF for each of the delta, which represents a probability, our current best estimate of that delta. We hope that when we run the iteration many, many times, these PDF of deltas, they will go thinner and thinner and thinner. Eventually, they converge into some sort of a delta function where we will arrive at the true value of the deltas. So along the time domains in each iteration, we do the following. We start from a PDF of the theta at theta k. Then we apply a noisy delta to arrive at the theta k plus 1 given theta k. This looks like the prediction step in a common filter. And then we used basically this predicted theta k map plus 1 given theta k as the fresh parameters and compute our control effort based on that. And after we apply our control effort and observe the yk plus 1, we use yk plus 1 as the observation and do the common filter innovation step to correct our theta k plus 1 given theta k into the new theta k plus 1. So really in time, the entire thing looks like it is a common filter where the input noises are now the noisy beliefs of the deltas, so the parameter drift, whereas the observations, the y's, they're the new observations. The state variables, they're all the thetas. So I actually tested this idea on a number of systems. I tried inverted pendulums. I tried a 2 degree of freedom sort of fully actuated robot. And I tried a sort of a toy example of a nonlinear system. And in essence, I arrived at this, which is a dead simple AIX model. I think this sort of best showcases what's currently working for the model and what is wrong. So this is a dead simple regression model. VK is the input. We're using this model to track a sinusoidal reference signal. And we use a one-step inversion controller with a reference pre-filter to control the sequence. And then we artificially mixed in measurement and input noise to the estimator. What we have found to come to find is that the tracking performance of our state estimation is actually really good. So a key thing here is that what we're really doing in this project is a state estimation. We can use any controller acting on a fresh variable as long as it's compatible with STR. So the best controller that would work will be something like an LQG controller that explicitly works on probability density function and is risk sensitive because we basically have a noisy belief of theta at every timestamp. However, in this project, we go for a simpler controller. And we find that as long as you tune the controller well enough, you're going to achieve good enough tracking performance. So the within trial performance is actually fine. However, the problem is I find that the system doesn't really work over the iterations. So what happens is as we iterate through each iterations, we use the past set of theta after iteration finish to compute a new set of deltas through a Bayesian inference process. And we then use that new set of deltas in a new iteration and then recompute the deltas once that iteration is finished. These deltas, our hope is that these deltas will go along the iteration domain and converge to their real true value. We come to find that they converge, but they actually converge to the wrong value. So we have identified the wrong parameter drift when where in our model, the drift should be that simple, should be zero, so there should be zero drift. And we fail to identify that effectively. So what can happen? What can go wrong in this entire thing? So one thing is that we have done one simplification when we're modeling the sort of the across trial updates of the parameter thetas. We have assumed that basically when one trial is finished, we have theta 0, theta 1, all the way to theta k. And then we have assumed that these are all independent. And because they're independent noisy observations, we use them to work out a new set of deltas that are basically noisy Gaussians. However, in reality, they're going to be correlated because you work out theta k plus 1 using theta k. So they're going to be positively correlated. Our algorithm effectively gets overconfident by neglecting the correlation. Apparently, the amount of correlation here is non-negligible. So that is one reason that can likely explain why across the iterations, our model of the drift, they converge but to the wrong value. The second thing that can possibly happen is sort of the noise of the regressor. So we use the past y's and past u's as our regressor. However, the regressor themselves are noisy. So that noise in turn gets used to estimate our parameter drift deltas, and those deltas are then in turn used to predict the next zetas, which are in turn used to compute the control effort. So that noise gets convoluted inside and may get amplified in these closed loop settings. That can be something that's actually quite big if the noise themselves are large. And the third thing, which is also a classical problem about adaptive control, is the dual control problem. Because in this test, we're tracking a constant signal, we're effectively sort of not exploring the full control landscape to make sure the system is as identifiable as possible. So that really is a trade-off between sort of your tracking a reference as closely as possible and then identifying the system as fully as possible. And because we fail to do that, that can also be a contributing factor to why we are modeling the wrong deltas. So our future work really just can be expanded on the three problems that I have identified. I believe this project is leading somewhere because the underlying mathematics, as I have written in my paper, are actually they look quite nice. It looks that they are promising. However, we must address the covariance problem to derive sort of an actual appropriate update of how to update our deltas across iterations to make sure that they actually converge reliably. And another thing to actually explore on is that instead of using STR, perhaps we should use full state space model. Those states are sort of they're more robust to noise because you filter them through input and output. So they might work better with this kind of inference settings. And the third thing that we can try is to, instead of tracking a constant signal, we mix in a bit of sort of excitation, for example, a smaller sinusoidal signal to the reference, and use that to excite the system to explore all the all the directions of this where the system can vary. That can also perhaps improve the performance of the state estimation algorithm.